The value of cosine of k pi, on the other hand, it may have a different value depending on the value of the index integer k, as I explained to you on the next slide. So far, the last equation that you see on the screen give you the formula for c tilde k. Now, let's see what can we do. The value, like I told you, of cos of k pi, it could be equal to either -1 or +1, depending on the index k. If k is an odd number, like 1, 3, 5, 7, then cos of k pi equal to -1. On the other hand, if k is an even number, like 2, 4, 6, or 8, then cosine of k pi will be equal to +1. So, because of that reason, we express cosine of k pi, this term right here, cosine of k pi, we can express as -1 raised to the power k. And the reason this term can be expressed like that is because, as you can see, if k is an even number, like 2, 4, 6, 8, then -1 raised to the power k is equal to a +1. But on the other hand, if k in here is an odd number, then -1 to the power k will be equal to a negative value. Okay? So cos of k pi can be expressed as -1 raised to the power k. So that equation right there can be separated into two portions for c tilde k. The first portion corresponding to the real part of the imaginary number c tilde k. The second portion that is associated with the I give you the imaginary portion of the c tilde k. Now, according to the definition of c tilde k that I have discussed with you a few lectures ago, the definition of c tilde k is given by equation 23 earlier that I repeated in here. So, if you compare equation 23, as you can see clearly, equation 23, it has two components. The first component is the real part, which is equal to a sub k over 2. That is a real component. The second component, it has the imaginary part, which is minus b sub k times I. Okay? So that is the so-called c tilde k. Now, if you compare the real part of c tilde k, which is the same thing like ak over 2, you equate that to the real part of c tilde k, which is this term right here. Then we can figure out the value of ak. Can you see that? So this is the real part of c tilde k. If we equate that real part, the real part of c tilde k, you equate that real part of c tilde k with this real part of c tilde k, then we can find out the expression for a sub k. And that expression is given right here in this equation for a sub k. Similarly, if you equate the imaginary part of the c tilde k, we equate that with the imaginary part of c tilde k, then we can obtain the formula for b sub k, and that formula is given right here. So now we have the formula for a sub k and b sub k expressed in terms of the integer index k. Now, if you let the index k going from 1 or 2 or up to 8, then we can calculate a sub 1, a sub 2 up to a sub 8. And the same thing we can calculate for b sub 1, b sub 2 up to b sub 8. Okay, this is the value of k. So, for example, when you let k equal to 1, k equal to 1, let k equal to 1, let k equal to 1, then we can calculate a sub 1. If you let k equal to 2, everywhere this formula, then we can calculate a sub 2. So by doing that, you can calculate all of the value of a sub k, where k go from 1 all the way to 8. bk, where k go from 1, 2, all the way to 8. And these a1 up to a8 that you calculated based on the previous formula that I show you right here, a sub k, b sub k, the answer you got will be exactly the same, identical, as we presented to you in my earlier lecture when we talked about Fourier series coefficient. In fact, that was the example number 1 that I talked to you earlier. So, after you already know A1, B1, A2, B2, A3, B3 up to A8 and B8, we can go back to the definition of C tilde k, as I show you in equation 23. So if you know AK and BK, we can easily calculate C tilde k, all right, based on equation 23. So we can easily say, knowing A1, knowing B1, we can calculate C tilde 1. And the answer for C tilde 1 is right here. And notice again, the first term minus 1 over pi represents the real part of the complex number C tilde 1. And the second portion, which is plus 1/2, represents the imaginary part. For the same thing, if you let k equal to 2, we can calculate C tilde 2 equal to A2 minus I B2 over 2. And since we know the value A2 and B2, we can plug it and then can say the answer for C tilde 2 is equal to this much. And so on and so on. We can calculate all the way for C tilde 3, C tilde 4, C tilde 5. Actually, you can see there's a pattern here. When this guy have the index and the subscript of 3, which is the odd number, the denominator on the right hand side is always equal to this term, which is like 3 square times pi. Okay? And for the imaginary part, when this guy is equal to 3, the other guy is always double it, so like equal to 6. As you can see the pattern right here, when C is the odd number, let's say k equal to 5, right? C tilde 5, k equal to odd number 5. The imaginary part, this term right here, the denominator, this guy is the same thing as 5 square times pi. And when this guy is equal to 5, the odd number, the denominator of the imaginary portion is always double, so 5 double becomes 10. On the other hand, corresponding to the index k equal to like an even number, like k equal to 4, then what's happening is the real part is always equal to 0, and the imaginary part, the denominator, is double it, so 4 becomes 8. So there's a pattern right there. Okay, that's C tilde 5. And you can see again on the next slide, when the index k equal to 6, which is the even number, the real part is equal to 0, like I told you, and the denominator of the imaginary part is double it, it becomes 12. And finally, is one more example, when k equal to 7, which is like an odd number, then the real part, denominator, this term right here is equal to 7 squared times pi, like I told you before. And the denominator of the imaginary part is double it. So 7 double become 14. So based on that pattern that we recognize, then we can write out the answer for c tilde k in a very nice compact form. C tilde k is equal to the first equation when k is an odd number. And as you remember, we have something like k, the index k now become k squared for the real part. For the denominator of the imaginary part, it's double it, become 2k. On the other hand, when k is an even number, then the real portion of c tilde k is 0. And the denominator of the imaginary part, again, is double. So this formula is very compact. And you can get the same answer for c tilde 1, c tilde 2, c tilde 8 using this compact formula right there. And that is the end of this lecture. Acknowledgement.